Aldehydes and ketones undergo many common reactions because they contain the carbonyl group, the C double bond O group. The first of these reactions that we're going to consider or recap is the reaction with hydrogen cyanide. Now, hydrogen cyanide is a toxic gas. So any reaction with an aldehyde or a ketone is carried out by preparing HCN in situ. And it's prepared in situ by reacting potassium cyanide with dilute sulfuric acid between 10 and 20 degrees centigrade. Now we're just first of all going to look at a reaction between an aldehyde and hydrogen cyanide, and the aldehyde that I have chosen is 3-methyl-butanal. So the aldehyde group, it's position number 1, so 1, 2, 3, 4, so it is butanal. And then the methyl group is on 1, 2, 3, carbon number 3, so it is 3-methyl-butanal. When you're figuring out the structure of the organic product, just break the C double bond O, which is what I have done here, and just reproduce the rest of the molecule. Then add the CN group onto the carbon and the H onto the oxygen. The resulting compound has two functional groups, the CN functional group and the OH functional group. But the CN functional group has higher priority than the OH functional group. So the name is, it's a nitrile. So it gets position number 1. So there's 1, 2, 3, 4, 5. So that's pentane nitrile. The OH group as a substituent is called the hydroxy group, and it is on carbon number 2, and the methyl group is on carbon number 4. H comes before M in the alphabet, so we put hydroxy first in the name and methyl second. So it's 2-hydroxy, 4-methyl, pentane nitrile. Now carrying out a similar reaction with a ketone, this time pentanthreone, and hydrogen cyanide. Again, to figure out the structure of the organic molecule, the first thing that you do is just reproduce the reactant, break the C double bond O, add the CN onto the carbon and the H onto the oxygen. Naming the organic product, again, it's a nitrile with the nitrile group being in position number 1. So the greatest number of carbons I have in a row, it's 4, irrespective of whether you go that away or that away. So it is butane nitrile. The hydroxy group is on carbon number 2. You'll notice that it's always on carbon number 2, so it's 2-hydroxy. We also have a methyl group, and it's also on carbon number 2. But this time E comes before H in the alphabet, so it's 2-ethyl, 2-hydroxy butane nitrile. So the alkyl group here comes first because E comes before H in the alphabet, whereas in the first product, H comes before M, so the alkyl group came second. You know that to make an aldehyde, you oxidize a primary alcohol, and to make a ketone, you oxidize a secondary alcohol. Therefore, it should come as no surprise that if you reduce an aldehyde, you'll get a primary alcohol, and if you reduce a ketone, you will get a secondary alcohol. Now, the reducing agent that is used to perform such a reaction is called lithium tetrahydridoaluminate 3, and it's also known as lithal. When we use lithal, it's very important to make sure that there is no water around, because there's a risk of explosion if there is. So lithal is always dissolved in dry ether, and the reaction is carried out under reflux. Now, thankfully, you don't have complicated equations to write. You can just use H in square brackets whenever you're writing the equation. Now, I've chosen to illustrate the reaction of an aldehyde being reduced. I've chosen 3,4-dimethyl pentanal. So there's 1, 2, 3, 4, 5, so it's pentanal, and the methyl on position number 3 and position number 4. Now, when you're figuring out what the reduction product is, just as you did with HCN, the first thing that you do, break the C double bond O and just reproduce the molecule with the C double bond O broken. And then one of the hydrogens adds to the carbon and the other hydrogen adds to the oxygen exactly the same way we did it with HCN, except that it was the CN that added to the carbon, whereas here it's another H. And do exactly the same with the ketone. Now, you should notice that there is a pattern in the names. So the 3,4-dimethyl pentanal reduces to 3,4-dimethyl pentan-1-ol. 3,4,5-trimethyl-hexane-2-on reduces to 3,4,5-trimethyl-hexane-2-ol. So if, for instance, we had 2,3,4,5 tetramethyl hexanal, it would reduce to 2,3,4,5 tetramethyl hexane-1-ol. Aldehydes and ketones also react with 2,4-dinitrophenylhydrazine. Now the structure is best remembered by building it up from this molecule, which is called hydrazine. And if you take away one of the hydrogens and then add the molecule onto a benzene ring, which as a substituent is called a phenyl group, then this molecule is called phenylhydrazine. Now if you add two nitro groups onto positions number 2 and 4, so the hydrazine, so there's the phenyl group, the hydrazine group is on position number 1, so there's a nitro group on position number 2 and a nitro group on position number 4. So that is the structure of 2,4-dinitrophenylhydrazine. When you're writing the reaction between an aldehyde or a ketone with 2,4-dinitrophenylhydrazine, draw the carbonyl compound with the C double bond O group facing the NH2 group. Then simply remove a water molecule. So there's where the water molecule comes from there. Then add the remaining bits of the two molecules together, and there is the structure of the resulting molecule, which is called a 2,4-dinitrophenylhydrazone. When you've done all the hard work and you have written that equation, which is frequently asked on A21 papers, please do not forget to write the water. You'll lose a mark if you do, and yet you've done all the hard work. Now notice the name of the compound. It's very similar to the name of the aldehyde or ketone. So the pentan-3-on product, just simply its name changes into pentan-3-on 2,4-dinitrophenylhydrazone. 2,4-dinitrophenylhydrazones are all orange or yellow solids. So if you have an unknown compound which you think is an aldehyde or a ketone, react it with 2,4-DNP, and if an orange or yellow solid forms, then you know that you do in fact have an aldehyde or a ketone. You could be asked a question to write the molecular formula for the 2,4-DNP derivative, or to work out the relative molecular mass. Be careful when you're doing this. You need to remember this benzene ring. It's the skeletal formula that's given here. So there are 6 carbons in that benzene ring. And you need to know that there is a H on each of those positions. That will become more clear whenever you have studied aromatic chemistry. So for the molecular formula of this compound, there are 5 carbons here and then another 6, so that's 11. In terms of hydrogens, there's 5 and 5's 10, and 1's 11, 12, 13, 14. There are 4 nitrogens, 1, 2, 3, 4, and there are 4 oxygens, 1, 2, 3, 4. You know that an aldehyde can be oxidized to a carboxylic acid, but a ketone resists oxidation. So therefore we use the oxidation reaction to distinguish between an aldehyde or a ketone. To carry out the oxidation, you can use any of these 3 oxidizing agents. And on a test tube scale, you just simply mix a few cubic centimeters of one of these oxidizing agents with a few drops of the aldehyde or a ketone, and then set the test tube in a hot water bath. And there won't be any reaction with the ketone, so you won't see any colour change. But with dilute sulfuric acid and potassium dichromate, the solution will change from orange to green. With the Fehling solution, you will see that blue solution changing to form a red precipitate. And if Tollen's reagent was the oxidizing agent that you used, then you will see a silver mirror forming. I've just written an equation here illustrating how a typical aldehyde would react with any of these three oxidizing agents. So I've used propanol as my example, and in the oxidation we can just simply use O in square brackets, and you can see the aldehyde being oxidized to the carboxyl group. So propanol is being oxidized to propanoic acid. When the aldehyde is oxidized, the oxidizing agent is itself reduced, and you may have to write the reduction equation for a specific oxidizing agent. So looking at the dichromate ion to begin with, and looking at the oxidation number, you can see that chromium's oxidation number decreases, and decrease in oxidation number is indeed reduction. Now, to write this half equation, you first must make sure that you have the same number of atoms of the element which has been oxidized or reduced. Chromium in this case, there's 2 chromiums on the left, so I need to have 2 chromiums there on the right. Now, +6 to +3 is decrease in oxidation number. Decrease in oxidation number is reduction. Reduction is gain of electrons. Going from +6 to +3 is gain of 3 electrons, but there are 2 chromiums being reduced, so that's gain of 6 electrons. Next thing you do is you look at the charge on both sides. So there is a charge of -8 on the left and a charge of +6 on the right. The charge needs to be the same on both sides, so to make the charge the same you can either throw in H+ or OH- ions. Since this reaction is carried out under acid conditions, it's H+ ions that you put in. So to get the charge the same on both sides, if you add 14H+ on the left, then that will now make the charge +6 on both sides. Now you will notice that you have hydrogen and oxygen on the left, but you have no hydrogen and oxygen on the right, so you can throw in water on the right to sort that out, and if you add 7 waters, then that will put the same number of hydrogens and oxygens on both sides of that half equation. So that half equation is now sorted. Fehling solution is blue because it contains the copper-2 ion in solution. And when you use Fehling solution to oxidize the aldehyde, the Fehling solution becomes reduced to a red precipitate of copper-1 oxide. So the half equation showing the reduction of the copper-2 ion is given like so. Tollen's reagent has Ag+ ions present in it, and during the reduction of Tollen's reagent, the silver ions turn into silver metal. So the half equation for the silver ions is shown like so.